Hey guys, I'm not feeling well. In fact, I'm sicker than I was before. So we're going to be doing this video lesson instead. So the notes for today are on the ideal gas law. This is the last gas law that you need to know. The ones that we covered previously were Boyle's law, Charles' law, Gay-Lussac's law, and the combined gas law, and now this is the last one that we're going to cover. As the name kind of implies, with the ideal gas law, this gas law is true when gases are acting ideally. So those kinetic molecular theory behaviors that we had talked about previously. Gases are mostly empty space. They move in that constant linear random motion. They don't lose energy when they collide with things like that. So what this ideal gas law does is it actually relates every single variable that we've talked about so far to each other. So you have pressure, that's represented by P, volume, which is represented by V, moles, so we haven't talked about moles yet with gases, which is represented by N. I have no idea why they picked N instead of MOL. That's weird, but now moles is N, okay? A constant, which is represented by R, that's also new. I'll talk more about that here in a second. And then temperature, which is represented by T. So when we're using the ideal gas law, a couple of things you need to be careful with. Temperature, like for all the other gas laws, has to be measured in Kelvin, okay? So you can't use degrees Celsius in this gas law. It has to be Kelvin. And as a reminder, to convert degrees Celsius to Kelvin, you just add 273, okay, to do that conversion. I'll come back and talk about the constant here in a second. Moles is just going to be moles, so just how many moles of gas are we talking about? That's what you'll plug in for moles. For volume, for the ideal gas law, volume has to be measured in liters. So you cannot use milliliters or centimeters cubed for the ideal gas law. And some of the other laws we talked about, as long as the volume units matched, it was okay, but for this one it has to be liters specifically. But what's confusing and frustrating about the ideal gas law is that for pressure, there is nothing that is standard. So for example, volume has to be liters, moles has to be moles, temperature has to be Kelvin. But for pressure, we can have a variety. We could have ATM, like we've discussed before. We can have kilopascals, which is kPa, or we can have millimeters of mercury. So pressure can be one of these three for the ideal gas law, but these previous ones do all need to be the same. So here's more about R, which is a constant. We haven't really worked with constants so far in this class. You might have seen them in other classes. For example, in physical science, you might have seen the letter G used as a constant. Whenever you saw G, you knew that you had to use the number for gravity. So the acceleration due to gravity, which is 9.8. So a constant is basically just a letter that is a stand-in for a number, and you just always plug in that number whenever you see that variable. Another good example of a constant is Einstein's famous equation equals mc squared. The E in the equation stands for energy. The M in the equation stands for mass. But the C is actually a constant, which stands for the speed of light, which is 3.0 times 10 to the 8th meters per second. So whenever you see C in an equation, that letter C just stands for this number. Obviously, writing the letter C is a lot easier than writing 3.0 times 10 to the 8th, which is why we use that instead. So a constant is just a number that makes the equation true. When you see that constant, when you see that variable, you just plug in the number. But, again, for the ideal gas law, if you remember on the previous slide, temperature is always Kelvin. Moles is always moles, volume is always liters, but since pressure can change in its unit, the constant used for R also changes. Because if you kind of think about it, if you remember, at room temperature, the pressure is usually like 1 atmosphere, In kilopascals, that's the same as 101.3. And in millimeters of mercury, that is the same as 760. So if I'm doing a problem with the ideal gas law, and if I'm choosing to use atmospheres, kilopascals, or millimeters of mercury, my numbers are totally different, which will then make my answer totally different. So since the unit of pressure can change, the R value also has to change. So what we have is we have 3 R values for the different units of pressure that we can use. So R, the constant, can either be 0.0821, or R can be 8.314, or R can be 62.4. And the number that you plug in for R changes based on what unit of pressure is being used. And if you have not already noticed it, you can figure that out by looking at the units after the number. And this is probably the most confusing thing about this, is what I just boxed in. These are the units for R, okay? Just like how if I were to write like 25 liters, liters is the unit. So this huge, gigantic thing is the unit for R. And the reason that's so big is because it helps cancel everything out. And I'll show you how that works here in a second, okay? But why don't you take a second and guess? Let's say I'm doing an ideal gas law problem, and I'm deciding to measure my pressure in atmospheres. Answer in your head really quick. Do you think I would use the first number, second number, or the third number? Hopefully you answered in your head that you would use the first number, because if you notice within that unit there is atmospheres. If you were using pressure in kilopascals, you would use the second number because kilopascals is in the unit. And then if you were using millimeters of mercury for your unit of pressure, you would use the third one because it has millimeters of mercury in it. So these numbers you don't have to memorize. They will be given to you on quizzes and on tests. So really the only thing you have to do is you have to decide which R value you are using for a problem. And now we'll look at an example of it, and that might help anything that might still be fuzzy with this. So basically, for the ideal gas law, if you know 3 out of the 4 variables, you can solve for the other one just using algebra. So what we have here would be a typical ideal gas law problem. So our question is, what pressure in kilopascals is exerted by 1.5 moles of hydrogen gas in a 0.300 liter container at 310 Kelvin? So for this, because there's so many variables involved, I think for this one you almost have to make the list on the side, figure out what is what, and then go ahead and plug it in. So I've got my ideal gas law down here, PV equals nRT. So over here I'm going to put P, V, N, R, and T, and then kind of go through my problem and figure out what is what. Okay. So first I'm going to look for P. And by looking at my question, it says what pressure in kilopascals. So that is what I'm looking for. Okay. That's what I'm trying to solve for. Note, this will be important later, that I want the pressure to be in kilopascals. Okay, so that's the unit I'm looking for. Then for volume, okay, I'll look for my volume. I've got the 0.300 liters here, okay. It's already in liters, so that's good, because for the ideal gas law, it has to be in liters. Then N stands for moles. Looks like I have 1.5 moles. Okay, and now R is where we need to go back, and we need to look at our previous R values. So our previous R values on the other slide were 0.0821, 8.314, or 62.4. The 0.0821 had ATM in the unit, 8.314 had kPa in the unit, and 62.4 had millimeters of mercury in the unit. So given this, and since I wanted pressure in kPa, I'm going to pick 8.314. So R will be 8.314. I'm going to plug in the whole unit for right now. So the unit for R is liters times kPa over moles times Kelvin. I'm going to show you how that plays out here in a second, okay? Then temperature is my last one, and that's 310 Kelvin. So now that I have all of my variables picked out, now I can go ahead and I can plug in, okay? So I'm going to put P, that's my question mark, times 0.300 liters equals N 1.5 moles times 8.314, running out of room. I'm going to rewrite this, okay. I'm going to go 1.5 moles times 8.314 liters times kPa over moles times Kelvin times 310 Kelvin. So that's me just plugging in my variables from the other side, okay? They're all next to each other, so they're all being multiplied by each other. So it's P times 3.00 liters equals 1.5 times 8.314 times 310. So P is what I want to solve for. So to get P all by itself, I'm going to divide by 0.300 liters on this side. So I'm going to divide by 0.300 liters on this side. Okay, and this is where I want to talk about how this unit for R makes sense. Okay, because when I have this big old unit for R over here, when it comes time for canceling things out, notice how my liters cancels out, my Kelvin cancels out, my mole cancels out, and then what's the only unit I'm left over here? kPa. And going back to my problem, what did I want to solve for? Pressure in kPa. So that's why that huge, gigantic unit is there. Like on a quiz or on a test, if you don't want to write that in that whole thing, that is totally fine. But that's just like the purpose that it serves. Okay. So I'm going to go ahead and I'm going to take 1.5 times 8.314 times 310, and I'm going to divide it by 0.300 liters, and I get, alright, when I type this into my calculator, I get P equals 12,886, okay, but, sig figs, 1.5 is 2. You can disclude the R value when you're looking at sig figs. Okay, so that is 2. 310 has 2, that's a tricky one. And 0.300 has 3, so my final answer should have 3. Shave, round up. My final answer is 13,000 kPa. Remember, that's the unit I wanted. Boom. That's the ideal gas law. Okay, let's try another one together. Okay, a gas sample occupies 2.5 liters. What is the temperature in K of a 3.5 mole sample at 1.2 atmospheres? So, write your variables on the side. So P, V equals N, R, T. Okay. So pressure, looking through this, looks like it's 1.2 atmospheres. Volume, looks like it's 2.5 liters. N is 3.5 moles. Okay. R, that's where you have to make a decision. Okay. So why don't you try to figure this out on your own? So why don't you pause the video, go back of 5 minutes or whatever, and try to figure out what R you think we're going to use. So pause the video and see if you can figure that on your own first. Okay. So the R value you should have gotten, since the pressure is in ATM, the R value that matches ATM is 0.0821. So that should be the number that you're going to plug in for R. And then temperature, that is what I'm trying to figure out. That's my question mark. Okay. So let's go ahead and start plugging these in. So we're going to have 1.2 ATM times 2.5 liters equals 3.5 moles times 0.0821 times T. Temperature is what I'm trying to solve for. Okay, so temperature is what I'm trying to solve for. That's what I'm trying to get all by itself. If I just want to do this all in one step and just going to be done with it, what I can do is I can divide by 3.5 times 0.0821. You can just do all of that at the same time instead of doing it in multiple steps. So if I do it on that side, though, I've got to do it on this side. So 3.5 times 0.0821. So what I'm going to type into my calculator then is I'm going to type in 1.2 times 2.5 divided by 3.5 times 0.0821. So with that, I get 10.44 equals T. Okay, but gotta check sig figs. So I have 2, 2, 2. You can ignore the R. So this should have 2. This is one of those weird ones where in order to get a 10, 2, I should do 10 and I should have a dot right afterwards, which then makes that 0 significant. Okay, and if I'm solving for temperature, remember, for the ideal gas law, temperature has to be measured in Kelvin. So this 10 is going to be in Kelvin. And that's going to be my final answer. Alright. So for this next slide, what I want you to do is I want you to pause the video. I want you to see if you can solve this on your own. And then once you feel like you've done this on your own, I want you to come back and push play. And I will have my answer and all of my work shown. But I want to see if you can do it on your own first. So this is where you should pause the video, and then in a few seconds you will be able to see the right answer with all the work on it afterwards. Okay, there you go. So my final answer was 0.2 moles. So a couple of tricky ones to be careful with this. The temperature was in degrees Celsius, remember, and we can't use degrees Celsius for the ideal gas law. It has to be in Kelvin. So you should have added 273 to get 308 Kelvin. That's one thing. The other one is making sure you pick the right R value. So because this is millimeters of mercury, you should have picked the 62.4 for the R value. Then the last one that's tricky with this is sig figs. 5 liters only has one sig fig, so your final answer should only have one sig fig. Zeros in front never count, so that's why it is 0.2. So why don't you go ahead and pause the video again? Why don't you give it one more shot on the next problem, and then after that you should be good to go. Alright, here's one more for you. A couple of things to be careful with this one. Again, temperature was in degrees Celsius, so make sure that you add the 273 to get that into Kelvin. Okay. The correct R value for this is 0.0821 because of the ATM for the pressure. And then checking your sig figs, you should have 2. So 57 liters is your final answer. Alright, at this time now, go ahead and switch to the next video where I will talk about how you're going to use the ideal gas law in your burning down the house project.